We're going to take a quick look at vertical springs, and we're going to pick up where we left off at the end of class on Monday, which, if you remember, was solving the supposed energy review problem to find the maximum compression distance of this spring. And we found that to be 0.581 meters, or 58.1 centimeters. This is something that we're going to need to use as we let this block enter simple harmonic motion. It's going to be a vertical simple harmonic motion. And again, we just need to remember this number as we move forward to the next slide. As it begins to oscillate, these are the four things that we want to find out about it. Remember, though, that we're going to start by looking a little bit at forces, a little bit of energy, and a little bit of simple harmonic motion, all three of these taken together. Let's start with the forces approach for part A. We've got this block of mass M, and as it oscillates on the spring, we have two forces on it. We have mg pulling down on this, and we have the restoring force in the spring pulling or pushing up on this, and that is kx from Hooke's law. These two forces, whichever one of these is greater, will determine the direction of the acceleration of the object. But when they are equal, that's when we're in equilibrium. Equilibrium is no net force on the object. Equilibrium is no net force. So these two forces must be equal for that to happen. When we look at part A, we want the compression of the spring when maximum speed is achieved. If we remember, max speed happens at equilibrium. So we need these forces to be equal for the max speed to happen. So when we take a look at part A, to get part A, we need to set those forces equal and just solve for the compression distance x. So that's going to be kx equals mg. We go back and check our info. So we can just keep that info here. Let me write that at the top because we're going to need that a couple times. K is 270 newtons per meter. Mass of this is 3.5 kilograms. So 270 times x equals 3.5 times 9.8. X, or the compression distance, should work out to be 0.127 meters, or 12.7 centimeters. So what this means is, as the block falls, the spring compresses to the max distance, which we said was 58.1 centimeters. It raises up into simple harmonic motion, and the equilibrium position happens not when the spring is completely uncompressed, but when it's at 12.7 meters of compression. Let's take a look at B, the amplitude of the oscillation. Using that same concept, the spring is going to oscillate between max compression, 58.1 centimeters, to equilibrium, 12.7 centimeters of compression, then up to the amplitude on the other side, and back to equilibrium, and it repeats indefinitely. So the amplitude of the oscillation is just a difference between the equilibrium position and the max compression or the max stretch. So all we need to do to find the amplitude is just find the distance between those two compressions that we have. It's our max compression minus our equilibrium compression, and our max compression is, we'll do it in centimeters here, 58.1 minus the 12.7 centimeters. Our amplitude of our simple harmonic motion is going to be 45.4 centimeters. 45.4 centimeters. Okay, and again, compresses by that much, goes to equilibrium, stretches by that much, goes back to equilibrium again, and oscillates again with that amplitude in simple harmonic motion. Now let's move on to part C, the maximum speed of the oscillation. When we do this, the easiest way to treat this is, again, going back to energy. The maximum speed of the oscillation, well, speed implies kinetic energy. It's a vertical oscillation, so it's going to be we know that's at equilibrium position, so it's going to be a little bit above its maximum compression, so it's going to have some kinetic and it's going to have some potential, gravitational potential. And our reference value, when we use conservation of energy to solve this, we should have, when the spring is completely compressed, only elastic potential energy if we take that point to be our reference point for measuring height. So our conservation of energy equation is going to say this. Elastic potential, when the spring is at max compression, is equal to the energy at the equilibrium position. Again, where max speed is achieved, that's what we're solving for. We have Ke there, and we have gravitational potential energy there. So, 1/2 K A squared equals 1/2 M V squared plus mg A. And for both compression distance and for height, I use the amplitude. Again, max compression is when it's compressed at the amplitude for elastic potential, and the height of the equilibrium position is, again, the amplitude, so I can use that here as well. I should know everything in this equation other than the velocity. I have 1/2 times my k, which is 270. Amplitude I found to be 0.454 meters in the last step. That gets squared. E equals 1/2 times 3.5 kilograms. V squared, my variable, plus 3.5 times 9.8. Again, my amplitude 0.454. I solve this for my velocity, and I find my maximum velocity should be 2.65 meters per second. To finish this up, we'll look at D. D is asking us for the period of oscillation. This is still a mass oscillating on a spring in simple harmonic motion. So in order to find this, we're going to go back to the hopefully by now familiar equation. Period for a mass on a spring is equal to 2 pi times the square root of m over k. Just the same as a horizontal oscillator here. So the period is equal to 2 pi times the root of 3.5 kilograms over 270 newtons per meter. My period, when I calculate this, should be 0.715 seconds. After you finish this video, you can email me with any questions. Please check on Schoology for the practice AP problem that uses vertical springs. Hopefully you'll find that it's fairly similar to this and really not too bad to work with.